some new material. So we mentioned this idea of non-classical light, which is going to be a big part of the subject matter of the first part of this semester. And what do we mean by that? Well, it's a bit of a tricky question. What we have discussed, and what we said, was that we have a coherent state is the state of the quantum field that is equivalent to having a perfectly stable intensity. Or wave. So if I had, after the state that was the state that has, whose mean value follows the classical trajectory, obeys the classical Maxwell's equations, and whose uncertainty is the minimum quantum values allowed by the uncertainty principle, then that is a coherent state. Okay? So what we mean by classical light, one way of defining a light as classical light, is if the state of the field, I'll just write it out first in words, the state is a classical statistical mixture of coherent states. So formally, that would say that the state is generally a mixed state, a density operator, written as a statistical mixture of coherent states with probability distribution P, and I'm allowing multiple modes. So this little bracketed alpha is the set of all alpha associated with all the modes. Okay? And what it means for this to be a classical statistical mixture is that this function is a positive function, non-singular, or not more singular than a delta function. So a derivative of a delta function would not be good. And as we have discussed in the past, such a state arises from, is generated from the vacuum if I have a classical current. So that's another way of what we mean by classical light. If I were to write down the Hamiltonian that coupled generally quantum matter to quantum light, and I started in vacuum and allowed the state, then I'd have some coupled, as we say, entangled state, generally between the quantum degrees of freedom of the matter and the quantum light, and it wouldn't necessarily end in such a state. But as we'll review this again, if we start with that Hamiltonian, we treat the matter as a classical current. If the current is perfectly well defined, like in a radio oscillator, then the state that's generated would be a coherent state. And if there's any kind of classical thermal noise, Johnson noise, what have you, on your current, then there would be a distribution of possible currents, and that statistical distribution of possible currents would lead to a statistical distribution of possible coherent states. And that's what we're calling classical light. That's the term we're using. That's classical. So one of the things that we discussed, or have discussed in the past, is what kinds of phenomena are smoking guns, if you like, or litmus tests that the state could not have been of this form. Okay? And so a state, light is non-classical, we're going to call it non-classical light. Cannot be expressed as a state of this form. So, phenomena that exhibit non-classicality that we discussed last semester so example phenomena that are litmus tests or that exhibit non-classicality. Number one, sub-Poissonian photon counting statistics. So if we have a photon counter and we send our light beam on this photon counter, we count for some time interval, we get clicks, we get some random clicks, and we ask if there's some number of photons that I get in that, then what we said is that if I had a coherent state, then we would have Poisson fluctuations, which is what you would expect for just completely non-correlated events of counting. You would have Poisson statistics. So what we know is for a coherent state, for say, let's just talk about a single mode of the field. We have alpha to the n over square root of n factorial to the minus alpha squared over 2n. This probability amplitude gives me the probability of counting n photons in that time interval that defines the mode. And that probability distribution is equal to the average n e to the minus average n to the power n factorial, where the average n is alpha squared. And for this distribution, this is Poisson, which means that the fluctuations in n is equal to the mean. So the variance in the number of counts you would get in any time interval would be equal to n. But what is the general situation? Well, if we have classical light, meaning that the state is of this form, well then we can calculate what the fluctuation in the photon number is. Let's review that. The variance in n is equal to the average of n squared minus the average of n squared, right? That's the trace of rho with the observable a dagger a squared minus the trace of rho with a dagger a, all quantity squared. And as we remember, in order to calculate the expected value of a polynomial in A and A dagger, when using a representation of the state that is expressed in this way, what we should do is we should commute all things in such a way as to put the observable in normal order, to put all the A daggers to the left and all the A's to the right. This, you remember, this particular distribution is known as the Glauber-Sudarshan P representation. We'll be talking soon about other kinds of representations like the Wigner function and the Buscemi function and their relations to one another. If we have a P representation of the state, then we calculate expectation values by normal order. So let's just do a little aside over here. A dagger A squared is A dagger A times A dagger A. And to express this in normal order, I'll commute this. So that becomes A dagger A plus the commutator, which gives me A dagger A. Okay? So this, just to remind you of this somewhat confusing notation, this is what's often called the normally ordered. Okay? So the double dot here means ignore the commutator and move all the A daggers to the left and all the A daggers to the right. Okay? So what we have is that the number operator squared is equal to the normally ordered version of the number operator plus this other term, which came from the commutator. Okay? Somewhat confusing. The double dot means forget about the fact that A and A dagger can commute. The reason we do that now is that if I now look at the expectation value of the number operator squared, which given this, right, that's equal to the trace of rho with that. So the trace of rho with that is equal to the integral over this, the trace of this, the normally ordered thing, plus that. And so the point of normally ordering is that because alpha, the coherent state, is an eigenvector of A, when we've written this in the normally ordered form, we can replace all the annihilation operators with alpha and all the gradation operators with alpha star. So this is equal to alpha star squared times alpha squared. And similarly, over here, this is alpha star alpha. So the expectation value of the number operator squared is equal to the statistical average of alpha squared to the power 2, alpha to the 4. I'll write it this way for reasons that are not quite as mad as my madness shows, plus, well, what's left over really is the average of n. Okay. So, coming back over here, what we have in this case is that this is equal to, again, this is the average of n squared. So this is equal to alpha to the alpha squared minus the mean of alpha quantity squared plus the average of n. Okay? So this term is this. This term is the first thing here, and then I have that last thing. And so, what we see from all of this is that for general classical light, that the fluctuation in photon number is equal to the mean n plus the classical noise on the amplitude, let's say the variance in the intensity. So that kind of makes sense. And actually it was sort of noticed by Einstein in the derivation of the Bose-Einstein statistics, because a thermal distribution, for a thermal distribution, for a Bose-Einstein distribution, which you will remind yourself about in homework, what you find is that the fluctuation in number is equal to average n plus the average of n squared. And Einstein kind of noticed that this is the part that's the wave fluctuation. It's the variance in alpha, and this is the particle part. There's sort of particle and wave nature in the uncertainty. Because the waves, there's thermal nature to the waves, there's always this in a thermal distribution. And then you have the irreducible sort of particle part, which is the fact that it's discrete. So what this says is that if this is a true probability distribution, if this is a probability distribution, then this variance is always greater than or equal to 0. In which case, what we know is that for classical light, this is always greater than or equal to the mean number, which is to say that for classical light, the fluctuations that I would see here would always be greater than Poisson statistics. Poisson statistics would be the case if it had a perfect intensity, having to do with the fact that the photons are discrete, and then any noise, classical noise on the laser intensity would give me additional fluctuations, which would make this super Poissonian. But if I see something which is less random than Poisson, then that could not have been associated with a classical statistical mixture of coherent states. Okay? So that's one of the smoking gun. Another is just to remind you quickly about that. God, we're going from polar vortex here to sauna weather. Is the business of photon anti-bunching. So another thing we studied last semester is the phenomenon that if I look not just at the photon counts in a certain time interval, but the correlation between when photons arrive. So if I sent a light beam on a beam splitter and I did this correlation that we remind ourselves of last time, the lay one, and then I look at the coincidence between them. And I look at that correlation. This correlation function was given by, as we discussed, it's an intensity correlation function, and by the Glauber photon counting theory, that's related to the normally ordered product of the two intensities for the two detectors. And if we look at the normalized version of that, which we call E2 of tau, which is the ratio of this correlation function to the product of these correlations, So the average of this times the average of this. So that's telling us if they were statistically independent, then the average of the product is the product of the averages, and this would be 1. Of course, if I have stationary statistics, then this doesn't matter when I measure the intensity. This is often written as over the average intensity squared. That what I find is the following. If I were to plot that as a function of tau, that if I have a coherence state with a long coherence time, that this G2 as a function of tau is 1 and flat. But if I have something which has classical statistical noise over some correlation time, as we discussed, then what you will find is that we see this goes up to 2. And this is what's known as photon bunching. So photon bunching says that G2 at 0 is greater than G2 at tau. Or could be tau could be positive or negative. It's actually a symmetric function. Meaning that they're more likely, the two photons are more likely to come together than they are separated. And this is really about Bose statistics. Okay, but if the state is classical, this must be true. So for classical light, we always see either this flat for the perfectly coherent or something which is slightly bunched if there is additional classical statistical noise on top of that. On the other hand, if we had something like a single photon state, well-defined definite number of photons, well then there's no chance of having the 2 clicks. In which case this would be 0. In fact, you see something that looks like that. So if we see anything that dips below 1, it doesn't have to go all the way to 0, but it might, then this is what's called photon anti-bunching. And photon anti-bunching is another signature of non-classicality. In fact, it was the first signature that was ever observed back in the late 1970s. Right, so these are examples that, in order to see photon anti-bunching, you need some kind of non-classical source. We discussed that at the very end of the semester, last semester, when we looked at the resonance fluorescence from a single photon emitter, like an atom. And that's because if an atom spontaneously emits, if I see that spontaneous emission, there's no chance of seeing another photon, because it's just one atom that emits. So it has to be re-excited, and it takes some time of separation. So looking for photon anti-bunching is a way of looking for something like single photon emitters. All right. So these examples are examples whose non-classicality is exhibited in photon counting. Okay, and so these are examples of non-classicality that are associated with what we just called last lecture the discrete variables. That is to say, the number of photons in a certain interval. What we're going to talk about today and for the next few lectures is signatures that are associated with the continuous variables. the things that have to do with the non-classicality of the wave amplitude itself. Okay? And what that is going to involve, I mean, these phenomena are exhibited in direct photon counting. So we ask photon or no photon. It has nothing to do with the phase of the field or the wave. So the kinds of phenomena we're going to talk about now are going to involve different kinds of detectors. Detectors that, a detection scheme that is phase sensitive, because it's going on to say something about the non-classicality associated not just with the discrete variables, but the continuous variables, and there's that phase number uncertainty that we mentioned. So what do I mean? Let's do a little further review about that in our center.
Can I ask a quick question?
Please do.
What's the difference between, are sub-Poissonian photon counting the same as photon anti-bunching?
Good question. No. So photon anti-bunching means the following, that G2 at 0 is less than G2 of tau. Okay? So if I do this correlation function and I find this thing dip when I normalize it this way, as was done by Kimball in his PhD thesis, then you exhibit, you say, yes, there was photon antibunching. However, that experiment showed super Poissonian statistics because in any time interval, the fluctuation in the number of photons that we're seeing was beyond Poisson, it was greater than Poisson. And in fact, it's very difficult to see the sub-Poissonian statistics for the reason that any time you have loss in the system, that tends to increase the fluctuation in the number of photons. So suppose I have here, and we'll talk about this, finite detection efficiency. And that's certainly true. Most detectors don't, if you send a photon onto it, it's not guaranteed you're going to see a click. So we can model that by saying there's actually a finite, infinitely perfect detector preceded by some beam splitter, such that sometimes the photon gets through the beam splitter, but sometimes it gets reflected. And that will add some randomness into whether the photon arrives or not. And so it tends to add, so if you had sub-Poisson statistics in here, your detection won't show it. And that's one reason in that particular experiment. And the other reason is that they were looking at, in the original Kimball experiments, they were looking at an atomic beam. And so you didn't have a definite number of atoms coming through your resonance fluorescence probe. So it's very hard. It's much more challenging to see sub-Poissonian statistics than it is to see anti-bunching. They're related, but they're not the same thing. Good question. All right, but now we're going to talk about another important signature of non-classicality associated with the continuous variables. So let's just review some of the algebra that we need in order to study such phenomena. So once again, as we said last time, so what we're talking about here is the wave amplitude, which we can think about as a phasor, right? And classically, we wrote that as a complex number, which we normalized this way with an amplitude and a phase, or the real and imaginary part that we call the quadratures, right? X is root 2. The real part of alpha, P is root 2, the imaginary part of alpha, and if I have a simple harmonic oscillator, then the phasor as a function of time is the phasor e to the minus I omega t, and the quadratures, so this is of course x cos omega t plus I, x at time t equals 0, cos omega t plus p sine omega t all over root 2 plus I minus x0 cos omega t plus p, I'm sorry, sine, cosine. And this is x at t. This is p at t. And the picture we have is this. Phasor going around. Okay? So these are our, and quantumly, quantumly, alpha goes to A, the quadrature goes to the position, and the other quadrature goes to the momentum. We satisfy the canonical commutation relations, or the boson commutators, as they're often called. Notes to remind myself what I'm talking about here. Right. Oh yeah, right. And then of course we also have the relation that the number operator has this commutator with the annihilation operator. All right. I think we're alpha squared. The intensity was like number up here. So some algebra we have, of course, we have something like a rotation operator in phase space. The phase space is the phasor space. And what is that rotation operator? Well, that's just that's generated by the number operator, J dagger A. So what is to say that if we look at the conjugation of the annihilation operator, which is like the phasor, just to remind you of one way to calculate that based on Baker-Campbell-Hausdorff is to write this in terms of multiple commutators. This is the commutator A, or middle A plus A with A plus a half A with A plus dot 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 and factorial n times multiple commutators, where big A is the exponent. So here, where I've written this as e to the A, e to the minus A. So in our case, A, in this case, is minus I theta n hat. So when you do that multiple commutator, of course, every time you commute, you get back the annihilation operator. And then you have n powers of theta. So this is equal to the sum over n minus I theta to the power n over n factorial times a, which is e to the minus theta a. So that's the rotation operator. In fact, we define that, then we have that the rotation, let us define x sub theta as the rotation operator acting on x through the conjugation and using x is equal to a plus a dagger over root 2. Then this is equal to x cos theta plus p sine theta. Yeah, that's what it is. And p theta is the rotated version of p. Which is minus x sine theta plus p cos theta. So those are the quadratures. If this is root 2x and this is root 2p, then somewhere over here are the rotated quadratures, root 2 x theta, root 2 p theta, rotated by theta. So it's a rotation of phase space. Okay. Of course, it's clear, because this is a unitary transformation, that x theta and p theta satisfy the same commutation relation as x and p, as long as it's the same theta. Okay, so that's one ingredient to remind ourselves of. And another piece of algebra to remind ourselves of is the phase space displacement operator. So another piece of algebra we have here is phase space displacement. Operator, also a unitary operator. D is a function of alpha, is defined to be equal to e to the alpha a dagger minus its conjugate, alpha star a, which is equal to e to the minus I x p hat minus p x hat. So this is a simultaneous, remember that x is the generator of displacement momentum, p is the generator of displacements in position, and so this is a simultaneous translation in position and momentum, hence the term phase space displacement. It's symmetric in x and t, neither is ordered before the other when it's up in the exponent like that. And this operator conjugates the annihilation operator. And then we could go through the same algebra that we just did, where we write, this is minus a, and we do that commutator multiple times. And what we find is that this is equal to a plus alpha. So it displaces the annihilation operator by this. Of course, this is times the identity. And it thus follows that this displaces the position by the real part and displaces the momentum by the imaginary part. Okay. Moreover, the coherent state alpha is obtained by displacing the ground state of the harmonic oscillator or the vacuum. It follows simply from these relations that if I apply the annihilation operator to this, that's the annihilation operator on the displaced vacuum, and I put in a d dagger d, then this is equal to alpha, okay, which is what we must have for a coherent state. And it's an eigenstate of the annihilation operator. So the picture that we have of the coherent state is that if this is the vacuum, then the coherent state is the displaced vacuum, displaced in phase space by that. Moreover, the fluctuations again, it follows from these expressions over here that the expected value of position is what is the real part of alpha, and the expected part of momentum is the imaginary part of alpha, and the fluctuations, the variance of x and p, are equal, and they're equal to the vacuum level, which with our normalization is a half. So for a coherent state, this uncertainty bubble has 1 over root 2 as its RMS in both x and p, and any other quadrature for that matter. In fact, this would be true no matter what quadratures we were choosing, because of the fact that the vacuum has no dependence on its uncertainty with respect to those quadratures. Okay, very good. Now, one thing a picture to keep in mind is, so this is, say, a coherent state. And as we said, the number operator is the generator of rotations in phase space. So if I started with the state of the harmonic oscillator that is a coherent state, and it's a free harmonic oscillator, then the state at a later time, of course, given by the Hamiltonian acting on the state at the initial time, is equal to e to the minus I omega a dagger, or omega t, times the number operator, right? Because h is omega a dagger a. I'm leaving my h bars out because I'm lazy. Acting on this, which is e to the minus I omega t, and the displacement operator acting on the vacuum, which is equal to the rotation operator rotated by the angle omega t acting on the displacement operator acting on the vacuum. Okay. Which is equal to, use this usual trick, sticking an r dagger r over here, is equal to the rotation operator by that angle e to the alpha A dagger minus alpha star A R dagger, and rotation on the vacuum leaves the vacuum alone. Okay. So now we play the usual trick of you can shove a unitary operator inside an exponent, right? And so that is equal to the exponential alpha r omega a dagger omega t a dagger r omega t minus alpha star r omega t a r dagger omega t acting in a vacuum. Okay. Now what? Well, we know what the rotation operator is. It unfortunately was erased. What we had was that r dagger theta a r theta was e to the minus I theta a, right? So we just had. So I ask you, what is this?
That's e to the I omega.
E to the plus I omega t, right? Because you got the dagger in the wrong place. So you put the dagger here, you make that minus. The dagger, you put that minus. And then this is minus. So that minus cancels that minus. This is e to the plus I omega t a. And this is, I'm going through this tedious calculation because this is the kind of calculation you're going to do a ton of this semester in homework. So, you know, kind of see it done once, maybe twice. You'll do it. And so this then is equal to the displacement as expected. So that is equal to the coherent state whose phasor amplitude is changing just as the classical amplitude. And so this thing is going around counterclockwise like that. In fact, every point inside this uncertainty bubble is doing that. And it's staying rigid. So if I were to sketch, as I will, what is the position as a function of time? Well, the mean value follows this classical trajectory, but then there's a kind of uncertainty band around this thing. Which is supposed to be equally thick everywhere. Because at every point when I project this onto the x-axis, it's the same band of thickness 1 over root 2. So if I were to measure, if I had to somehow could do a projective measurement of the quadrature x at any time, I would see a particular realization that might look like this. I mean, it's supposed to be single value, so. In other words, there's noise that is sampled from this distribution. This is the vacuum noise. The coherent state has the same level of noise of the vacuum on top of the mean field. So if you were able to do a measurement of this quadrature, this is one realization. And then I do another realization, I get a different one, sampled from a distribution which, as we know, is Gaussian. Because the harmonic oscillator, the ground state of the harmonic oscillator has a Gaussian distribution of positions, right? It's a Gaussian wave packet. And so this is what's called Gaussian white noise. So this is the coherent state. Now what we want to talk about is something that is non-classical in the sense that it has noise that's less than the vacuum level. That's what we want to understand. Because if I added additional statistical fluctuation of the mean field on top of that, of course I get more noise than the vacuum. The vacuum would be irreducible. So if something is going to have noise below the vacuum level, that can't be from a classical statistical mixture of these things. Okay? And so that's what we want to look at. So the state that is the first thing to consider is what's called a squeeze state. So what's a squeeze state? Squeeze state of a harmonic oscillator is it's a state of the simple harmonic oscillator that satisfies the minimum uncertainty product but with fluctuations in one quadrature below the vacuum level. Okay, so a squeeze state satisfies delta x, delta p equals a half. But delta x for some theta is less than 1/2. I mean, you could say or equal to, it would be, you know, if you want to call a coherent state a squeeze state with no squeezing, yeah. Okay, so what we want to study is the algebra of such states. And then we're going to want to understand what their physical properties are and how do we make them? Where do they come from? And what are they good for? All right. So, let's see. So, let me think about the order in which I want to do this.
What was fluctuation in one quadrature?
Okay, what does that mean? So a quadrature, remember, I guess I didn't read it right. The term quadrature. So the quadratures are the variables x, the observables x and p for some theta. Okay. So what I mean by this is that the state, the squeeze state psi, is such that the variance of this is less than half.
Okay, so when you say one of the quadratures, you mean one of x or p?
What I mean is for some theta.
Yeah.
Okay. Remember, it could be x or p or some rotated x. Remember, p is just x rotated by 90 degrees anyway. So that's what I mean by that. So, for example, an example such state. Suppose I'll just draw it here in phase space, a state that has this elliptical type uncertainty. x dp, where this uncertainty is less than 1 over root 2 as an RMS. I'll call that e to the minus r over root 2, and therefore the product, this guy, is e to the plus r over root 2. Okay, so that's squeezed. You know, this was the vacuum. And then I squeezed it. Matt, it's one for your YouTube noisy.
Yeah. I have to make a whole montage, so we have to build them up.
Collect them all.
Yeah.
All right. So, right. So what? How do I? So that state is a squeeze state, and it doesn't have to be at the origin. I mean, I could have a state like that, which is like that, or it could be rotated at some angle relative to the mean. So it could be like that. Okay. As long as the product of these two semi-minor axes equals a half. That is. So let's just firstly think about why such a state must be non-classical. I claim if this is true, then such a state cannot be thought of as a statistical mixture of coherent states. Well, let's ask the question. If I have, so let's look at a case of the one like we drew over here, where this guy, just for simplicity, let's look at the case where x, I'm squeezed in x. So I'm squeezed along the x quadrature. So the fluctuations in x are given by the mean of x squared minus the mean of x quantity squared. Okay. And this is equal to the mean of a plus a dagger over root 2. So I'll bring out the half. Minus squared. Okay. And again, if my state is equal to a statistical mixture of coherent states, then in order to calculate these expectation values, I should re-express these operators in normal order. I should commute everything to put it in normal order. Okay, so let's do that once again. So this is equal to a squared plus a dagger squared plus a dagger a plus a dagger, right? That's what's inside there. And so to normally order it, I want to commute to put all this, make this on the left. So this becomes a squared plus twice a dagger a plus 1, which is equal to a plus a dagger squared, normally ordered, plus 1. Is that clear what that notation means? I find that always confusing. Right? This is saying ignore the commutators, and if I did that, this is what I'd have. But what's left over is the thing that came from the So with that said, what we find is that delta x squared is equal to equal to 1/2 plus 1/2 times the fluctuation in the real part, or one of them. No, that's right. We were talking about alpha squared. There, put half of there. The point here is that this, again, is always a positive number. It's the fluctuation of that. It's the real part of alpha when I replace that. And this is always positive unless I have a coherent state, in which case it's equal to 1/2. So as intuitively we said, there's no way that you can get below the vacuum level for a quadrature fluctuation if you have a coherent state and or any statistical noise on top of that. So if we're going to have a squeeze state, it's going to be something that's related to a non-classical type phenomena, not a classical current. All right, let's get a little bit more intuition about these states. So let's draw a couple of examples of these squeeze states, and let's draw the same kind of picture for what, say, the position quadrature is as a function of time. So for example, we drew the case where we had a coherent state. Let's take the case of the vacuum. That's a coherent state. So this is the phase space picture, x and p. And let's look at, for this state, what is the, if I were to measure the position quadrature as a function of time, what would I see?
Just random.
I'd see noise, right? Just noise. And I mean, what I can think about is that, you know, each phasor in this little probability distribution is moving around at, you know, with omega t, but it doesn't matter, it's just randomly sampled. So there's going to be, you know, there's a kind of noise variance here on top of it, but, you know, see, noise, okay? But with sort of equal variance at any time. So at any time I looked at what, I would do another sample, I'd get another noise sample, I looked at what, and I'd histogram up all of the different possible x values. What I find on average, I get 0. Sometimes I get a little bit above, sometimes I get a little below, and the RMS will be the same. It will always be 1/√2. And it'll be Gaussian distributed. Okay? What about if I had something that looked like the squeezed vacuum? By the way, this is sometimes called zero-point motion, right? Now what's going to happen? Well, again, each one of these points is going around with angle omega t. So what will I see? I'll see noise around 0, but the RMS will not be the same. There will be a phase dependence to my uncertainty. So if I were to look at what the position of this was as a function of time, on average it would still be 0. At this point, I see less noise, and then I'll see more noise, and then I'll see less noise, and I'll see more. So the sort of the picture of the variance of my Gaussian will look like this, and I'll see, noise, and I'll see a lot of noise, and then a lot of noise, and that will repeat. Okay? And what is the period of this change in my uncertainty? Well, it's going to be half the period of the oscillator, right? Because the fact this goes back to itself after pi, right? So this is, if this is omega t, then this is pi over 2. 3 pi over 2. 2 pi. So there's phase dependent noise. What about this state? Let's say I had a state that looked like this. It had a mean field, but the uncertainty is smallest perpendicular to alpha, okay? And its greatest, the uncertainty is smallest along alpha and greatest perpendicular to alpha. Such a thing is called, in comparison to the coherent state, this thing is known as an amplitude squeeze state. The amplitude is squeezed. My uncertainty in the amplitude is less than it is for the coherent state. Okay? Now, again, all of this flies around at omega, angular velocity omega. So if I were to plot this, measure in a projective measurement, x, as a function of time, what would I see? I'm being cavalier with my square-roots of 2. Please forgive me. Well, when this thing crosses the axis, right, when x is at its maximum value, I have the minimum uncertainty. When it's at p, which means when its amplitude is 0, it will have the biggest uncertainty, right? So what it will look like is the following. Again, the mean field, is just the harmonic oscillator. But the variance, unlike the case of the coherent state, which had an equal uncertainty, the uncertainty in this value was the same no matter what the phase of the oscillation is. This thing has phase-dependent noise. It has the least noise here and the most noise here. So it looks kind of like this. Oh boy. Yeah, okay. So, more noise. So the point here is that little noise, lots of noise, little noise, lots of noise, little noise. With these kinds of, this is better drawn in my notes. Okay, so my uncertainty in the amplitude is least. Is that sort of clear? And that's what's known as an amplitude squeeze state. Finally, and then we'll just close there. We can have the opposite extreme. The case where I have whatever my mean field is, and my squeezing is the most perpendicular, and I have anti-squeezing along. Okay? Compared to a coherent state, this is known as a phase squeeze state. So this is phase squeezed. Okay? That's the jargon is supposed to amplitude speed, because we kind of know the phase better than the amplitude. And if I were to attempt to draw what's going on for this guy, again, I have the mean field does the same thing. But now it's the opposite. I have the least uncertainty here and the most uncertainty here. So I have something that kind of looks like this, where I have lots of noise, lots of noise, lots of noise. Okay? And we have phase-dependent noise. These pictures were first illuminated by someone known as C.M. Caves in a seminal paper in 1981, thinking about squeezing. And as you can see from this, there is one of the motivations for thinking about squeezing is in using, for example, laser fields to probe, say, motion inside an interferometer. If you can reduce the uncertainty, say, in your amplitude or phase, you can have higher precision measurement. So one of the things we're going to study towards the end of the semester is the application of squeeze states to metrology, and how one can try to beat what are called the standard quantum limits by employing things like squeeze states. Okie doke. So where we're headed, what we're going to do next time is write down, well, what is such a quantum state? How do I write it down algebraically? What are some more of its properties? And how would we measure this? Because, as I said, in order to do this measurement, I need to have some kind of detector that depends on the phase of the field, because this is a phase-dependent phenomenon. And the direct photon counting doesn't depend on the phase. It only depends on the magnitude of the phase. So we'll talk about that next time.